All right, are you ready? Here comes lysozyme. And lysozyme is unique because it is going to have a residue that has a pKa shift, so an atypical protonation state based on what we might expect. So what is lysozyme? Well, lysozyme is an enzyme that's going to break, it's going to hydrolyze the glycosidic linkage that we see in bacterial cell walls. So bacterial cell walls, you can think of them sort of being like 3-ply. We're going to have a carbohydrate sort of mesh, we're going to have a peptide mesh, and then we're actually also going to have disulfide linkages that happen. So if you want to break apart bacteria, you want to kill them, you need to break apart their cell wall. So this is part of sort of a generalized warfare system, sort of your innate immune system that's providing defenses against foreign agents. Okay, so this is a natural antimicrobial agent. We have a lot in saliva, mucus. Think about those tissues that are interacting directly sort of with the outside exterior world. Lots of it is actually in egg white. A lot of it in egg white, actually the importance of kind of maintaining a sterile environment as that chicken is growing. So lysozyme, again, one of those well-studied enzymes. What we're going to see here when we look at the enzyme active site, I want you to think of it like a mitten that has this substrate binding cleft. So again, not a very large protein. We're going to see several disulfide links. Importantly, there is going to be a glutamic acid residue that is pKa shifted. We'll talk about how, where, and why. Okay, but here's kind of an important piece that's going to play into what we see structurally. Has a very prominent substrate binding cleft. So I want you to think about like a mitten, that our substrate is going to come in and bind there. So I'm going to zoom in here so that we can see this. So here is, it fits about 6 residues of a carbohydrate polymer. Okay, and we're going to have the D and the E residues, so the 4th and the 5th residues, we're going to cleave in between them. And here in the enzyme active site, importantly, we can see a glutamic acid residue and an aspartic acid residue that are going to help facilitate that chemistry. Okay, so we're going to flip to a few other slides here, but I want you to remember this picture of our substrate binding cleft and our polypeptide that's in there. And importantly, we're going to be focused around the structure between the 4th and the 5th residue. And one of the things that we're going to see is that, remember, this is carbohydrates, so we're going to have 6-membered rings, so we're going to have chairs, and we're going to see a difference in this 4th ring, this D ring. We're going to see a different conformation than our typical chair conformation. Okay, so let's take a second, like we've done with our other enzymes, and start first by looking at the uncatalyzed reaction. So just to orient a little bit, this one I don't have the entire structure drawn because it just gets too complicated if we have that. So remember, when we talked about what we do when we cyclize sugars, that's taking one of the alcohol groups on sugars and either the aldehyde or the ketone that we use to kind of connect those together. That's how we form our anomeric bond. That's how we cyclize our sugars, okay? This is the bond that we're going to be talking about here. When we take and we polymerize those sugars together, we create an acetal or a ketal, and now we're going to be forming that glycosidic bond. That's how we polymerize sugars. And so this is the bond that we're talking about cleaving, what we refer to as the scissile bond. So that's the bond that we're going to have, that we're going to cleave. So walking through the chemistry that happens, okay, so look at what we've got here. We're going to have protonation of the guy that we want to be a leaving group, okay? This is the bond that we want to break, theme that we see mechanistically. If you want a bond to break, protonate the guy that you want to be the leaving group, okay? Now, leaving groups don't tend to leave. We tend not to see carbocations in our biochemistry mechanisms, okay? It's going to be forced out by something nearby. So in this case, we're going to have that oxygen, that's the ring oxygen in our cyclic sugar, okay? We're going to have formation of a pi bond here, and that's going to allow departure of that protonated leaving group, that good leaving group, okay? Second step now is we're going to have water come in here, nucleophilically attack that very electrophilic carbonyl carbon that's got a positive charge here on oxygen. We can return those electrons back to that oxygen, and now we get to our hemiacetal or hemiketal, depending on, again, whether we started with an aldose or a ketose sugar. Okay, some important pieces to sort of highlight here. We want to protonate this guy as a leaving group. So having something that can facilitate that protonation is going to be important. Note here that we're generating, after we have this guy leave, we're generating a very positively charged intermediate. So anything that we can do to help stabilize that is going to be important, okay? But as we always see with these mechanisms that involve hydrolysis, we have to have water come in at some point. Water tends to be nucleophilic when we see these chemistries, and so we can make it be a better nucleophile by deprotonation. So again, amino acid residues that could help with protonation, help with deprotonation, we're going to look for those when we look in the enzyme active site. Okay, remember those 3 steps that we have for performing chemistry. Chemistry on the substrate, use all your reagents, and then make sure you return your enzyme site to its active state. Okay, so you can see after we do this first step here, after we have this leaving group leave, we've broken this bond, we've done chemistry on the substrate, but we haven't yet involved water, and we haven't regenerated the enzyme active site. Okay, so that's going to be happening again in our stage 2. So I'm going to zoom in and focus on what needs to happen for this chemistry to happen. Now we've sort of ignored sort of some of the aspects that need to happen to have, the formation of a pi bond here, right? We really haven't thought too much about that, but we're going to think about that, and we're going to think about what it means to form a pi bond, because pi bonds are formed by side-to-side overlap of unhybridized sp2 orbitals. Oh boy, thinking back to molecular orbital theory from Gen Chem. So stick with me. We're going to kind of go through this slowly here. So one of the things that we need to identify is to why we have this half chair conformation. So I'm going to highlight a few things to see here. So notice again, here's these 6 residues of this polypeptide. Remember, they're sitting in that cleft that we have there. So remember we talked about cleavage happens between the 4th and the 5th residues. So this is where lysozyme is going to cut. So there's our glycosidic bond that's going to get cut. But look at this. This is weird, right? We've got what we call a half chair conformation. That doesn't sound normal, right? Chair conformers are the most stable conformation. This is actually something that's quite sterically strained. So there must be a reason for doing it. Okay, so I'm going to come back over here. We're going to highlight the reason why, and then we're going to kind of come back to this picture. Okay, but we're going to be looking at why we see this half chair conformation. So we're going to be looking in this region, this D ring, and it is in what we call a half chair conformation. So here's that half chair conformation. Okay, that's sterically strained. That's going to be entropically unfavorable to introduce that steric strain and hold that in an unfavorable conformation. Okay, so why do we do it? Okay, we're going to get into some more details on the next couple of slides, but to give you some a highlight, so we're going to say see next slides. Okay, for why. But to give you sort of the punchline, we must have that carbon and that oxygen be sp2 hybridized so that their p orbitals can overlap. So we must have our carbon, and I'll highlight where these carbon and oxygen atoms are. These carbon and oxygen atoms be sp2 hybridized, okay, so that their p orbitals can be in the same plane. Okay, and that being in the same plane means that they can overlap and form a pi bond. Okay, so maybe you remember this from Gen Chem. When we talk about the formation of bonds, sigma bonds are single bonds, and they are formed from end-on overlap of hybridized orbitals. When we have pi bonds are formed from side-to-side overlap of unhybridized p orbitals. So we need to have these p orbitals be in the same plane so that they have the right geometry to overlap and form a pi bond. Okay, so I'm going to highlight a couple of things here. This carbon and oxygen atom, okay? This is this carbon and oxygen atom, right? We are forming a pi bond right here. So let's find where these are here, okay? I'm having problems zooming here. Okay, it is this carbon and that oxygen atom, right? Those are the ones that need to overlap, okay? So how do we get them to be in the same plane? We make this half-chair conformation. Okay, we're going to see more of that on the next slide, but when we make this half-chair conformation, it allows all of these guys to be in the same plane. My iPad is really touchy right now. It does not want to zoom in and out. Okay, theme that we've seen again, anytime we have something that is an energetic penalty, if you will, a cost, we need to have some type of a gain. We need to have some type of an enthalpic compensation. Okay, so there's several favorable side chain interactions. One that's shown here, I'm going to highlight here. Okay, actually there's two of them that's sort of shown here. We've got a glutamine. We're going to talk about this valine 109, but those are going to be something that provide favorable interactions when we form this half-chair conformation. So entropic penalty from a half-chair conformation, enthalpic compensation by having new intermolecular forces, again with this valine and this glutamine that provide new hydrogen bonding interactions with that exocyclic CH2OH group. Okay, last little thing to map on here. I know there's a lot with these enzyme active sites. Okay, I want to highlight the important residues that we're going to see that are participating in chemistry. They're all highlighted in blue that you have there in this figure. It might be a little bit difficult to see, so I'm going to highlight them in different colors. Okay, obviously we saw this D residue in that half-chair conformation. Okay, so we've got that highlighted there. I want to highlight now glutamic acid 35. Okay, so I'm going to zoom in over here and we're going to see where this glutamic acid is right here, and we're going to see something unique about it. Okay, do you see that it has its hydrogen on there? Okay, it's protonated. We would not predict, based on a pKa value for carboxylic acids of 3 to 5, that we would not predict that that would be protonated. But in the enzyme active site, it is, and so it's able to act as a general acid catalyst. Okay, so this glutamic acid 35 has a unique pKa shift. Okay, and so that increases its pKa value, and so it remains protonated. Okay, next guy I want to draw your attention to, okay, is we've got this aspartic acid 52. Okay, zoom in the enzyme active site. Sure, here we go. Here's this aspartic acid 52, right next to the developing positive charge that we're going to have right here. Okay, and we're going to see when we zoom in and look at our enzyme active site and detail it, what's actually going on there. Okay, and then the last thing, we've actually highlighted one of these two residues already that's responsible for enthalpic compensation, but we've got this valine 109. So let's go through and just write a few details here. So aspartic acid 52, it's going to play a unique role. It's going to be a covalent catalyst. I'm going to zoom in one more time and kind of talk you through what's happening there. And then this valine is important for enthalpic compensation. Okay, so let's zoom in here and look at this aspartic acid residue. Okay, now what's really interesting is in the 20 plus years that I've been teaching biochemistry, it's actually changed what they thought that residue was doing. See if you can follow the logic here. Now we know that these lone pairs of electrons are going to form a pi bond here. That's why those two orange atoms are overlapping, right, or in the same plane, so that we can have that pi bond be formed. And then we're going to have this bond break. Okay, that's going to result in a positive charge that we're going to have in that area there. The original thought for this aspartic acid was that it just helped via electrostatic catalysis, so that it just was like, hey, positives developing here, negatives developing, or not developing, but negative is available here. It's going to soften that charge development. What we now know, because of experiments that have been done in the lab, is we actually know that we form a bond between that aspartic acid residue and this part of the substrate. So we're going to see that when we look in the enzyme active site. But that's just kind of an interesting story that, as little as 20, 30 years ago, they did not know exactly what was going on. I know a lot with Lysozyme here. Okay, we're going to move on now, and we're going to talk about a little bit about why these must be in the same plane. Okay, so remember, this is talking about that purpose of that half chair. If we're looking at what's happening here, this is our ring. Okay, so this is going to be our 6-membered ring. There's our oxygen. So let me just draw that out here. It's going to disappear in a second. But here's our 6-membered ring. So this oxygen is that oxygen. Okay, this carbon is that carbon. And then the rest of the ring is right here. So this is our cyclized sugar. And then when we have this guy, and that disappears, then we're going to have our glycosidic bond that hooks it to the next sugar. That's that. Okay, so orienting you to what those pieces are. When we think about this as a ring, it's going to be a chair. Okay, and I want you to think about sort of a chair, like literally like a lounge chair, right? It's got 4 atoms in the middle that are going to make a seat. It's got 1 atom at the point. It's going to be my headrest, and then 1 atom that's at my feet. It's going to be my footrest, right? When we think about a chair, right, we've got 4 atoms here that are going to be all in the same plane. We've got a footrest, and we got a headrest. What happens with a half chair is I'm going to move this footrest up so that all of these atoms are in the same plane. That's how a half chair works, okay? So when we have that half chair, now this footrest is now in line with my seat. Okay, I've lifted up my feet in my chair so that my foot is in line with that seat. And that is what allows for that proper overlap, that coplanarity that's going to allow for that pi bond formation. That only happens if I'm in a half chair conformation. So that's why we have that half chair conformation. Okay. Otherwise, we'd have a carbocation that we could not properly stabilize, okay? So if we just had this leaving group leave, there'd be a positive charge on that carbon. Not good. What we're going to have is we're going to have then these electrons are going to be able to form a pi bond that distributes that charge, gives everybody a complete octet, and that is much more stable, okay? So that is, again, the purpose of that half chair. Whew, that was a lot. Okay, so whole point of this is to have that half chair to be able to stabilize that charge development that we're going to have that's intermediate, that's going to be positively charged, as we're going to see in a little bit. What we're going to have is not water come in yet. We're actually going to see our aspartic acid come in there. We're going to see that in our enzyme active site. Okay, so if you didn't see that well right here, don't worry. We're going to see it when we map on our enzyme active site. Okay. So I'm going to zoom in here so that we can see these spots. We can see that this is not the 2 sort of step process that we saw with RNase. This is a little bit more involved. So let's follow along here. I'm going to start with step 1. Okay. Looking in our enzyme active site, when we start, we've got an empty enzyme active site that has glutamic acid that's in its protonated state. We talked about in another video why it's in its protonated state is it's got sort of a nonpolar, greasy environment that we have there. So it's actually more stable for it to be protonated and uncharged in that nonpolar environment. And then down here, we've got an aspartic acid. So we're going to bind that substrate polysaccharide, okay? We're really only looking at the 5th and 6th residues here. We're going to have that D residue that adopts that half chair. You don't really see that half chair conformation when we look at things as Hayworth projections. Okay, but this is the bond that we're going to be cleaving. That is our glycosidic bond that's going to be broken. So if we look at and we sort of try to detail the enzyme active site here, we can talk about this first step, because this first step is kind of important. Binding of that polysaccharide to the enzyme induces that conformational change in the D ring, making it into that half chair. It's going to be stabilized via that valine 109. We don't see that here, but we've set up a situation where now we are ready to have these two atoms be coplanar and able to stabilize the resulting positively charged species. Okay, so next step here, start with where your arrows are. Okay, now it might be a little bit weird because you're like, well, my arrows start here, but I thought I needed to start at an amino acid residue. So go ahead and start at an amino acid residue. There's only 2 arrows that we have here. So we're going to say glutamic acid 35, acting as a general acid, okay, serves to protonate the glycosidic oxygen. Is actually protonating this oxygen right here. So it's protonating that glycosidic oxygen, facilitating the cleavage of that glycosidic bond and the generation of what we call an oxonium ion transition state. Okay, that half chair is facilitated in its transition state stabilization by proper orbital overlap. So let's see if we can see that. So running through again, this proton is going to end up going to this oxygen. This is going to be our leaving group, so we're making it be a better leaving group. Okay, we end up with this intermediate. Now again, these electrons here need to come down and stabilize that. We do not want to have a carbocation, highly unstable. But the only way that those electrons are going to be able to come down and form a pi bond is if we have all of these atoms that are shown in red here be coplanar. That only happens if we have a half chair. Okay, so this is a transition state. So we really aren't officially stopping here because remember, transition states are sort of the peaks of hills. So what happens here is we want to readily stabilize this. Now, remember I told you it used to be that the thought was that like magnets, this negative charge would get close to this positive charge and help kind of just make it happier. That's not what happens. What we actually see is nucleophilic attack by this aspartic acid residue here. And that's actually going to stabilize this. So again, this positively charged oxonium ion transition state is going to be stabilized by aspartic acid acting as a covalent catalyst and forming a covalent, what we call glycosyl enzyme intermediate. Glycosyl meaning that sugar piece and the enzyme intermediate. Highlighting it used to be thought that it was just electrostatic catalysis, but now we know that we actually form a bond between our enzyme and the rest of this substrate. Okay, so what we're going to see here is we are going to have, and they don't really show it very well here. Let me zoom out and just make sure. Yeah, here they show it up here. We've got departure here of this downstream portion of our cleaved polysaccharide, and so now we've got this oxonium ion transition state that is stabilized by aspartic acid participating as a covalent catalyst. Okay. So now we're down to an intermediate, highlighting that things that are intermediates are isolatable, but things that are transition states are not. Transition states represent tops of hills. Okay. Now, once we've had sort of this departure of that downstream polypeptide, okay, now we've got this covalent intermediate, there's room for water to diffuse into the enzyme active site. So water is going to diffuse into the enzyme active site, and look what we have here. Remember what we started out as? Glutamic acid was protonated, not in its proper state right now. Aspartic acid was free, not in its proper state right now. And we hadn't yet involved water. Remember what we have in Act 1 and Act 2. Act 1 is chemistry on the substrate. Act 2 is use all reagents, and often that water, which is the second reagent, is used to regenerate the enzyme active site in its active state. Okay, so glutamic acid 35, acting as a general base, serves to deprotonate the incoming water, okay, increasing its nucleophilicity to attack on this glycosyl enzyme intermediate. We're going to release the aspartic acid from the enzyme, and that does 2 things. It regenerates glutamic acid as well as that aspartic acid residue. So coming back up here, we now have the rest of our product diffuse away from our enzyme active site, and we are back to our enzyme active site having everybody in the correct protonation states. Wow, I know that was a lot, but that was lysozyme and how it does its chemistry.